So let's do problem 15 on page 323. It says a discus thrower accelerates a discus from rest to a speed of 25 meters per second by whirling it through 1.25 revolutions. Assume the discus moves on the arc of a circle of 1 meter in radius. Calculate the final angular velocity, the angular acceleration, and the time it took. So let's set this up with given. So we've got this thing that's being whirled around and let go. So it goes through the initial velocity of the disk. The initial equals 0, and it goes through 1.25 radians. So when it's right here, it's got a final velocity of 25 meters per second. And and so this is, I'll just do this. This is delta theta equals 1.25 revolutions. Remember, revolutions is just a measure of angle. So you can treat it as this is our angular displacement was 1.25 revolutions. And this is kind of a little spiral. If it goes more than one revolution, it's kind of a nice way of showing that little trick. And then we know the radius r equals 1.00 meters. And what are we trying to find? Well, we're trying to find the final angular velocity, which we call omega. And B, we want to know the angular acceleration. And C, we want to know how much time did it take to do all that. So let's solve it. Well, for part A, I want to know the final angular velocity. Now, I don't know time yet, so I want to use one of the. So I'll probably do this. I'll probably say, okay, omega squared equals omega naught squared plus 2 alpha. Oh, wait, I don't need to do that. Hold on. I'm sorry, I'm being stupid. I forgot that what's given. The final linear velocity is given, 25 meters per second. So I can figure out the final angular velocity because I know that linear velocity is related to angular velocity by r omega. So that's kind of a basic equation you need to know. And so omega is equal to v over r. So omega is equal to 25 meters per second. And then r is 1.00 meters. Now watch this. This is one way to think of r. It's kind of like saying meters per radian. Okay, I think if you change it to an angular thing, if you have one radius wrapped around the circle gives me 1 radian. So you can almost think of the radius as being a conversion factor from linear stuff to angular stuff because it's meters per radian. So that cancels, and I get 25 radians per second. And that's my answer for A. And by the way, sometimes you'll see the book write it like this. Have you ever seen that? For the units, seconds to the -1. Radian is dimensionless. So, I mean, you can write it down, but you don't need to. You could just say 1 over seconds or seconds to the -1 power. Okay, part B. Now I can use the kinematic equations. I want to know the angular acceleration. I don't know the time, so I want to use the equation that doesn't have time in it. Okay, this is 0, so I can solve for the angular acceleration. Now, please don't talk right now. I'm almost done. Delta theta, because we know this, we know too, we need delta theta. Well, it's 1.25 revolutions, but I know 1 revolution is equal to 2 pi radians. So delta theta, when you go through that, is when you do this math, I believe you get 7.854. At least that's what Larry got, and I trust him. Okay. And then, so now I can use that in here. 25 radians per second squared over 2 times 7.854 radians. And that will get you an alpha of 39.7 or 39.8 radians per second squared. So that's my answer for part B. So you had to use the kinematic equation. You had to change from revolutions to radians to get that. Now for part C, which I'm going to have to squeeze in here, you want the time. You can use the first kinematic equation, or you can use the second, whatever you want. You can go omega equals omega naught plus alpha times t. So the initial angular velocity is 0. So alpha is equal to omega over t. And I'm sorry, what am I doing? Okay, I'm thinking about something else instead of what I'm doing. All right, so time is equal to omega over alpha here. And so the time is equal to 25 radians per second divided by 39.8 radians per second squared. And look at the units. Radians sort of cancel, okay? Sort of. And then the seconds cancels the second squared. You have 1 over seconds, which is seconds. Let's squeeze that in down here. You get 0.628 seconds. So let me zoom all the way out so you can see the whole thing. Okay. Any questions? Yes.
I use like a different equation. I think I use like.
Okay, hold on. That's all.